welcome back to another video. Today I want to show you how you can make this basic flight controller. We'll be going over how to do the schematic, PCB routing, and a basic test of its functionalities.
Okay, so what do we want to get out of this development board? So the idea is that it's going to be based on the STM32. That'll be because of its much higher power compared to other microcontrollers, and it's also fairly cheap. And to keep things simple, we'll have an accelerometer, gyroscope, and a barometer. That'll be so we can measure values without having to have an external sensor. Typically, with these flight controllers, you have a few extra communication ports so you can add different peripherals in as you need them. And then finally, we want a USB port so we can read all of our data back to a computer. For the objectives, we're going to go for a very small size because that means a very small weight. Yeah, we're also going to keep it as simple as possible. That image you see here on the right, this is the original prototype for the board, which had a few issues due to the complexity, so we're deciding to not go with this SD card this time. And I'm also going to make the board a lot smaller. And I'll show you how to do that, how to cram it together really well. But the first attempt wasn't too bad. Alright, so now we're going to head over to STM32 Cube ID. Obviously, we need to start from the microcontroller. So I'm going to click here, Access to MCU Selector, and we can choose whichever microcontroller we need. As you can see, it lists every single product that STM ST has made. But in our case, decided to go with the F426 RE. Choose it from here. You can see it for 10,000 of them. It's only $3.85 each, so that's pretty good. So yeah, once you select the microcontroller, you hit Start Project. And there we go. So now we're into this interface. So right now, I guess our priority is the communication interfaces first off. Select those by going System Core. We do want a debugging system. So we'll go with serial wire. And then connectivity. We'll go with USB on the go full speed in device only mode. That way we can upload firmware to the board through USB if we want. From there we can choose all the other peripherals we want. So accelerometer and gyroscope, they're going to be through I2C. So we can select those here. Select I2C and you want to enable just I2C. Click that. And it'll automatically assign the pins for you. I can enable all the parameters we want. And I'm going to try to use as many pins as possible. Okay, and then we can select our timers. So typically in flight controllers, PWM is one of the methods that you could use to control things like servos, receivers, and other devices. So since this is meant to be kind of a simple flight controller, we're going to want to have quite a few servo outputs. The goal is also to power this whole board using the battery eliminator circuit, or BEC, from an electronic speed controller. We also need to have some PWM outputs to control those ESCs. So we can go to timer 2, and we can see that each timer has multiple channels. So you'll have one clock source, but you can have 4 different, outputs from it. So yeah, we can choose channel 1, and we want PWM generation. You see it automatically defined it here. Alts and arrangements, there's several different ones. And obviously you need to play around with this and find the best outputs. One thing we need too is an external clock source. So STM32 has multiple internal timers, but if you have an external one, it'll improve the accuracy a bit. So yeah, if we go into high-speed clock, high-speed external, we can enable, and we're going to go with a crystal ceramic resonator. So we've got every single communication interface pretty much. Now we can define some general purpose input-output pins as well. And there we go. So that's pretty much everything. We have we have 3 UARTs, 2 I2C interfaces, 2 SPI interfaces, 8 PWM outputs, and then I think it's 6 GPIO outputs, 2 GPIO inputs, and 2 analog to digital converters. The next part is the clock, of course. So it's already asking me. This is where you will decide how fast the board should run. So here is the high-speed external crystal that we're using. This is the input frequency. So it's anywhere from 4 to 26 megahertz, but a typical value we'll use for this board is 8 megahertz. This to be done using the high-speed external. And now we can click this button. It'll resolve all the clock issues automatically. Okay, so it's finally done. It took almost 5 minutes, but we can see that we ended off with a frequency of 72 megahertz. So that's the frequency that the microcontroller runs at when it's in operation. And it can do 180 megahertz max. And yeah, that's all you need. That's all you need, yeah. So then now that that's fixed, we can do a code generation. Just click the button and make the code. Yeah, you need to make a project name and fill this out, of course. Okay, so now that we're in KiCad, we can go over the main schematic for this flight controller. So first off, we're going to start off with the power supply for this board. So like I mentioned earlier, it's going to be powered through the electronic speed controller's 5 volts. So we're going to have 5 volts in, and that will power everything that we need. We're going to be using just some standard 3-pin connectors here. And this will be PWM signal sent from the microcontroller to the outputs, and this will allow us to control our motors. Aside from that, we're also going to want to do USB power. So when we're testing it on the desk, we can have our computer power the board, and we won't have to worry about setting up any electronic speed controller. So the 5 volts from the USB is going to go through a poly fuse to make sure if something goes wrong, it doesn't burn our computer. And then it'll travel down here in parallel with input from the speed controller, enter in through a 3.3 volt regulator, and go to the rest of our electronics. So in the USB section, we have our 5 volt bus here. We're connected the differential pair like so. These two registers are pulled low. We're going to be using USB 2.0 just to keep things simple, full speed. KiCad's notation for this is to use a plus and a minus to signify that it's a differential pair. Lastly, the reset button. We have just a 100 nanofarad debouncing capacitor. That'll make it so that the microcontroller won't accidentally measure any additional inputs on the reset line. So for the accelerometer, I decided to go with the ICM-42670P. It's a very up-to-date accelerometer gyroscope, and it's fairly cheap too. Of course, in the manufacturer's website, you can always find any of the information you need for sensors like this. So we have the data sheet we can look at, the ECAD model, and any additional information. Bosch Sensor Tech. For the barometer, I went with the BMP390. This is the latest version out from Bosch Sensor Tech, and it has an overall resolution of plus or minus 25 centimeters accuracy, so it's quite good for the price. So I decided to use a single pole double throw switch here. So by flicking it high, we can program, and then by low, it just runs the default code already on it. Yeah, so with the high-speed external crystal that we're going to use, typically they're most commonly available in these 4-pin packages where 2 of the pins are ground and the other 2 are the crystal. So then, of course, we need our load capacitors, and then this value will get calculated based on your load capacitance of the crystal and any additional stray capacitance from the PCB. So what you can do is you can go to a website such as ECS Inc. International, and you can find all kinds of these calculators in order to calculate your load capacitance. So in our case, it was 20 picofarads. We can use our estimate of, say, we can just say 2.5 picofarads, and then we'll get that we should have 2 capacitors rated at 35 picofarads each. So that's an important calculation you have to make if you want your clock signal to be stable. All right, moving along, looking at the analog inputs. So since this is a flight controller, we want some way to measure any battery voltages or just any analog signals in general. So we're not really going to be measuring anything high frequency. So now, of course, here's all the other communication ports. We have serial wire debug enabled. I decided to use just the generic 2.54 millimeter pitch Arduino style header pins to make things just easier to work with. CAN bus for evaluation, SPI 1, SPI 3. We're gonna have 6 servo outputs. So the way I want this to work is that you can take just a standard 3-pin servo connector and plug it into the board, and you can use it very easily. You have 3 spare UART headers, and then just some general GPIO pins. And yeah, that is the schematic layout of the development board. Okay, now that we're ready for the PCB routing, there's going to be a very long montage. The actual PCB routing itself took around 3 to 4 hours, so it's impractical to go over the whole thing. But if you want any more information at any particular points in the montage, just slow down the video and you can see what's happening. Also, feel free to ask in the comments as well. Here's our final board layouts. So our input power comes from the ESCs. You just plug it into this 3-pin connector, 2 of them, and we can also power it through the USB. And then the rest of these pin sockets are all for the external communications. And we also have serial wire debug headers right here. Once you have your bill of materials ready, all your files generated, it's time to head to a manufacturer. Here's where I'd like to thank the sponsor of today's video, Pcbway. They did an excellent job on the flight controller that you saw in the beginning of the video, and you'll see just a minute now. It's very easy to use their website, so all you do is head to their homepage. You can get an instant quote here, so we can type in our dimensions. Use 5. Oops, this is a 4-layer. So yeah, it's very easy to use their website. You just select how many pieces you want, amount of layers. For this PCB, this is all just the defaults. Choose the solder mask, and it'll give you an instant quote. They also provide assembly services, so in case you can't do it yourself or don't want to, they can make the board. They have a minimum quantity of 1. And I believe right now they have a special offer for $29 for your assembly from 1 to 20 pieces. But I found their services to be extremely good and highly recommend them. And the finished PCBs I was genuinely impressed with.
Yep, and here is the output. That is the finished board. Hope you enjoyed this video and you learned something new. And hopefully this can help you in any one of your projects. As always, thank you for watching, and have a good day.